Good afternoon. Today's podcast, we are going to look at an example of utility theory in travel mode choice. This is one of a series of lectures in transportation engineering prepared for the final year students of the University of the West Indies Department of Civil and Environmental Engineering. To get us started in the concept of mode choice, let me ask you a very simple question. How did you get to campus today? What mode of travel did you use to get to campus? Did you perhaps come by car, either as a passenger or driver? Did you come by maxi taxi or minibus? Perhaps you came by one of the regular full-size buses of the PTSE. Or perhaps you took some exercise and decided that you were going to cycle. Or maybe you decided to walk with a group of friends or by yourself. Whichever mode you chose, there are some things that I'm sure that you would have considered in doing that. Some things that influenced your choice. Perhaps it was how much time it would take to make that journey. Perhaps it was the cost that you would have to pay to make that trip. Or perhaps you're looking at the security, the comfort, the convenience, something else that would have made it your personal choice. The thing is that all of these things could, in some combination, influence our choice of mode. So that brings us to the objectives of today's podcast. At the end of the podcast, you are going to be able to see how a simple model of modal choice can be used to simulate how commuters trade off time and cost in making their modal choice decisions. You're also going to see how the effect of policy decisions on travel choices can be estimated. So let's start by looking at the question of that model. We are going to be looking at a generalized cost function, and I'm going to explain what it's all about. Let us understand that we travel because we want to be somewhere else where we have a higher value. However, that travel itself puts a negative consequence on us. There's a disutility or negative consequence because we have to spend time, we have to spend money, we are going to experience some discomfort, maybe waiting or standing, and therefore there is a negative consequence of our choice. The modal choice model says basically that given that the trip must be made, a commuter will choose the one with the lowest disutility, so the lowest negative consequence. So that's our model, and we are going to look at that utility as a linear combination of all of the cost components that are affecting our choice. But these are not just going to be simply added in a linear way. They are going to be weighted by a parameter that reflects the relative importance of the attribute to the commuter, so that we are going to define our utility function as part of our modal choice decision. Let's see how this works in a binary example where we are going to just look at two attributes. So let's set it up this way. We say the utility for person I, that is utility of choice for person I, is a linear function of the attribute x weighted by the weight AI. So AI is the weight of attribute x1 for person I. BI is the weight of attribute x2 for person I. And we, of course, would understand that those weights are based on some empirical analysis of past travel choice behavior. In our case, x1 is the variable that defines the cost of the trip, and x2, the variable that defines the time spent traveling. So here we have set up our modal choice model in terms of the utility function, ui equal ai x1 plus bi x2. We have defined ai and bi as parameters of that function, and we have defined x1 and x2 as the cost of the trip and the time spent in the trip. So let's now see what our sample of persons that we are going to look at in terms of the trip making, what a sample looks like. We have three persons in this sample. Person one, who we call Busy Betty, has an A of -1 and a B of -2. Person two, who we will call Broke Barry, his A is -3 and his B is -1. And person three, who we know as Steady Sam, his A is -1 and his B is also -1. So looking at these weights for these three different people, can we deduce some of their characteristics? For instance, if I were to ask, who is the more money-conscious person, or who is the more time-conscious person, or who is neutral between time and money, what would the weights tell us? Well, the person who is most concerned about money would have a higher weight attached to that attribute, and that person, of course, is person 2, Broke Barry. The person who's more time conscious has a higher weight attached to that attribute, and that is the person 1 who is Busy Betty, whereas Steady Sam, good old Steady Sam, is neutral between time and money. So now we have defined our sample of people. We have our utility model. Let's put them together. Let us superimpose one on the other and identify how we can use the model to predict and explain the modal choice behavior of these three people. If we did that, we need to get some more information. We need to understand what are the actual attributes on which we are going to judge the modes. So in this case, our modes are car and bus, and the attributes are cost and time, as we said before, where a car costs 3 and a bus costs 1. And that could be the dollar cost, $3 for a car trip and $1 for a bus trip. And in terms of time, the car takes 1 unit of time, whereas the bus takes 5 units of time. And we can define that unit of time as an hour, let's say. It could be a half-hour unit, but it doesn't matter because what we are really looking at is the relative weights of the attributes. So that now we have all the elements that we can use to project what the utility would be and therefore what the mode choice of the persons would be. And we do that by substituting this information into the utility choice model. So we're going to pause the slide for a few minutes and allow you to try your hand at calculating these utilities. So now we're back. Well, let's see if you got the results that we came up with. What we found is that person 1, Busy Betty, has a U car of -5 and a U bus of -11, so she will choose car, the least negative consequence. Person 2, who is Broke Barry, has a U car of -10, a U bus of -8, so he will choose bus. Best alternative for him. Whereas for Steady Sam, his U car is -4, his U bus is -6, and as a consequence, he will choose car. So that given those characteristics of the modes car and bus experienced by persons 1, 2, and 3, given their weights that they attribute to those things, we will see that their choices may vary. The question is, can we change those choices? What are the possible options we have for changing the modal choice of these individuals? Well, if we want to change the modal choice of person 2, who is very cost conscious, and we want to shift him from bus to car, we are going to have to find a way of decreasing his cost of car ownership and car operation. Not that it's necessarily a good thing, but I'm just saying that's what is possible. What about the person who is time conscious, person 1? Well, she chose car because she's time conscious. So if we want to cause her to change her mode, one of the things we may have to do is to decrease the travel time by bus for that person in order to change her mode. But those are not the only things we can do. Can you think of 2 other things we can do to cause that shifted mode of those 2 persons? And what about person 3? How do we shift his mode? Let's see what you can do for that. What are our key takeaways? Well, we realize that people trade off time and costs to determine modal choice. We also recognize that that choice relates to both the modal attributes and the traveler attributes. So that when we are actually trying to understand the impact of policy decisions on the transportation system, we need that understanding of the choice behavior of the commuters and how they respond to various characteristics of the transportation system. Indeed, a very interesting element of modal choice modeling. What's next for us? Well, next time we meet, we're going to look at the treatment of uncertainty, errors, and randomness in travel choice behavior. We're going to introduce that uncertainty and that stochastic nature, and we are going to see how we can account for it. Some additional readings: Traffic and Highway Engineering by Gabel and Howell, and Transportation Engineering and Planning by Papakostas and Prevodoros. So until next time we meet, have a good day. Bye.